Hello and welcome. It's the second time we are talking to you from Dubai for Pi and AI Deeplearning.ai event. We will start with the welcome video from Dr. Andronik, and then we will continue. This session, it will be on YouTube Live. We have to cover 4 pillars. We'll talk about this after the welcome video.
Hello, deep learners. I'm Andrew Ng, founder of Deeplearning.ai, and I'm excited to welcome you to our global deep learning. Hey, Ken. So do you want to tell the people at Pine AI what you're working on?
Yes, sure. I'm leading a project called Workera, focusing on helping people get offers in AI and navigating their career by testing their skills, preparing for interviews and certifying them, as well as matching and referring them to good jobs in AI.
That's really cool. And what's the most exciting part of your day?
You know, the AI field is new, organizations and jobs are still misunderstood. So I'm excited to help people understand what different types of jobs exist in the field, what tasks they will work on, and what skills are needed to achieve those tasks.
That's really important work. Well, it's nice chatting. And now let's go chat to Hotel, who is on their product team.
Hey, Andrew.
Do you want to say hi to our friends at Pine AI and let them know what you're working on?
I would love to. Hi, everyone. I lead the product team in Deeplearning.ai, where we create AI education content accessible to people all around the world. People like you.
And what are you most excited about right now?
I am so excited to see our community grow and to see how eager people are to learn more about AI.
Thanks, also.
Thanks, Andrew.
So, as you can see, our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So if you want to build a career, you can leverage online resources available, including open source code, datasets, papers, and online courses like a deep learning specialization on Coursera. As part of this journey, I hope you get your hands dirty too. Don't be afraid of diving in to build your own project, or go ahead and try to replicate a research paper that you're excited about. One thing that I've seen help a lot of people succeed is if you can build a community or find a community of fellow deep learners you can meet with and study with on a regular basis. In fact, I hope that this Pine AI meetup that you're at right now will be a good place for you to meet these people. I hope you enjoyed the event today and that you learn a lot, both from the talks and from each other. And once again, welcome to the Deeplearning.ai community.
Gate, you are not audible. Gate, you are not audible.
Thank you, Ronak. I hope you enjoy the video. Today we are trying to cover AI for medicine from research to production. So that means we want to cover the points that if you are doing the research, what point you have to cover, and then when you go to the production part, what point you have and what challenges you have to go with. Mainly, we are focusing on four pillars. Let's say first about the scientific material or the academic material, which is the research itself, and then what is the software techniques and architect has to support this AI research. Also, let's say what is the challenges that we face when we are deep diving with this AI for medicine research, and then also what is the approval policies and organization part that we have to cover. So to do that, we have two samples we are going to cover. The first one is from our organization because this event is with partnership with AI.Hub. So Ronak will tell us about the first, let's say, trial, the first sample that we have for today. And the second one, it will come from John. I will move to Ronak immediately and I will ask him to start. Welcome, Ronak. And after the speech itself, for sure, we will be open for the questions. Welcome, Ronak. It's your time.
Thank you, Gate. Hello, everyone. I hope everyone is safe and sound. And I hope that this war which we are fighting will be over soon and we will be back to normal. But yes, I hope that there are some positivities in the new normal which we have. We are able to spend quite of the quality time with our families, and that is what we can enjoy as of now. So to come to the topic of the uh, webinar, let me introduce first myself. My name is Ronak Dangi. I currently resides in India, and I have around 12 years of experience altogether in multiple fields, including financial operations, digital marketing, insurance operations, sales support, sales servicing, and currently I am co-founder of Golden Bird Staffing Solutions, where we are providing remote staffing solutions across the world. Also, we have founded AI Hut with an vision to solve the problem of masses by bringing economical solutions and products which are positively impacting the masses across the world through artificial intelligence. So basically, the idea behind AI Hut is that there are so many problems which we can solve through machine learning, deep learning, and we are focusing specifically on those problems which can impact masses. And in this whole process, we started with obviously COVID AI, where Gate and our team. So Gate is the mastermind behind the uh, technical part of the AI, where we are using CNNs to identify COVID through radiology or X-rays for that matter. So we have achieved 99% NPV in this case, where it's like the like in simple word, it means that we are 99% sure in individual probability that a person is not having a COVID. That means that we are 100% sure of going to the market and saying that if we test anyone, the person is not a COVID positive person. Uh, Also, in identifying COVID, because it's all mathematics and probability. So in identifying COVID cases, we have achieved individual accuracy of 98.6%. That again means that we can use this product as a preliminary check, which is currently required uh, for the uh, for the inspection of COVID cases across the globe. So to give you to give you a brief about it, like we started with a problem statement. When we sat on the table, the problem statement was that we don't have enough infrastructure or capabilities to test masses, because like if I only talk about India, there are around 130 1.3 billion people altogether in India, and the front fighters of COVID are around more than 10 million for that matter. Now, the per day testing capacity of India is just around 125,000 people. That means that if even if like we have to test all the people who are on the frontliners in every 7 days, then we are having a deep shortage of testing COVID facilities, like testing the masses at the end of the day, because there is only one thing which can prevent spreading COVID, is to test more, identify the people who are having coronavirus, and isolate them. That is the only thing which is prevailing. And even if we increase it by 10 folds, there is a necessity to identify alternative and quick ways. Also, the cost effective way to do it. The reason I'm telling is that the current PCR test, which majorly all the governments are following, they cost around $500 normally. I'm really sorry, around $50 normally. So that's a big money at the end of the day. Where if I talk about globally, around 100 to 120 countries are not having the infrastructure either, or not having that much capabilities economically, because there is a very big burden into it. I was recently in talks with one of my friends in Canada, who is basically Nigerian. He was saying that Nigerian government is not testing at all because they don't have the kits and they don't have the economic power as of now to test it. That's the biggest or the saddest thing of like which I have listened to in past so many days, because like that's totally inhuman according to me. I'm not blaming Nigerian government for it, but still the problem lies is that they don't have the economic capabilities to do it. So here we came to a solution where we started with a very small team of three people, me, Gaith, and we brought in Dr. Rajendra Pamecha to give a small brief. He is a MD in ophthalmology, and he is one of the best experts, having around 40 years of experience in his life. So we bring him as a medical consultant to identify the feasibility of the project, and then we started working on it, where Gaith digged into some of the researches, developed his model, trained his machine to identify and uh, bring the solution to a level, or the research to a level where we can develop ultimate product out of it. So to be like, for the people who are looking for startups or who are looking to build something on their own, my suggestion is to start with it, try to build something, and then take it to a level where you need more hands, and you can test it and deploy it to the market. So currently, if you talk about our solution, we are at a live testing uh, development stage, where we can 100% like we are 100% sure that our product is ready to go for market. What only thing we need is basically the approval or the testing procedure from the governments. So this is what we are looking at, that this is the biggest challenge, that go to the right channels, approach the governments, and getting the end approval, or like asking them to have a look at our product. So the challenge is because they have multiple priorities and they have multiple functionaries at the end of the day, because what we are doing is one of the very unique ways now to and they are like, they have multiple kind of options. So reaching the right network and the right people where we can deploy this product is very much important at the end of the day. And this is what we are looking at in current scenario. So I am open for any one of you, if you have some connections or communications with the government bureaucrats across the world. I suppose that at least 140 countries in the world are in need of the product, which Gates will explain in detail after my part gets over. So this is the whole idea. Also, I talked about some of the challenges which are there, that is like the testings are costly, the time taken to do it or the facilities to get the test done are very limited. So once a person is tested, they have to wait for just 3 days. Also, the infrastructure facilities are not there. There is a long queue which needs to be reduced, and what we thought of from this project is, or the product is, or the solution is, that we can help governments, because I suppose that in India, it's a very big country with a very big population, but still in every village or every city, small or big, we have at least X-ray machines available. That's why we focused only on X-ray to get the accuracy through deep learning and machine learning, and we can we are quite sure when we say that we can 100% accurately identify whether a person is COVID or not. If it is so, the probability of identifying a person who is not COVID is far more important than a person who is having COVID, because if a person is getting positive, Ramiz, this thing will be explained by Gates in total. I just want to brief you about the business part of it so that you understand the how, if you are looking for some business propositions, how you gonna do it that ways. So this is what the idea is. So basically, uh, this radiology cost is any which ways on an average around $10 to $15, not more than that, because this is just a software and a person who is doing it can be easily implemented. There is no kind of very big training which has been required. What we are looking currently is collaborations with the government, where we can test run this on a live platform with just around 3,000 or 4,000 X-rays. We are ready to deploy it in any part of the world. So the authentication check or the live testing part is the only thing pending from the product point of view or from the deployment point of view as of now. So this is what it is, and I think that this is just a starting for AI Hut, where we are basically focusing on solving real-time problems of not only COVID, but there are so many diseases which can be identified through radiology or some other sense where we can use AI and machine learning to get the accuracy, to reduce the cost, and to mass deploy the solution at the end of the day, which do all goods to the world. And this is what the vision is, and this is what we are aiming every single day to achieve from AI.hut. uh, this is all from my side. I'm totally open for all the questions from all of you, and
Okay,
over to
Ronak,
you.
I will suggest us just to go for my side first,
Yeah.
and then we will be open for question. I received a question from Remis and you answer it.
Yeah.
But there is something, because today I was planning to have a special guest with us, Dr. Yusuf Al Assaf, from
Mhm.
the president of Rochester University.
Oh,
It
great.
seems that he didn't join us on Zoom, but he is watching us on YouTube. So he just
I am
sent.
with you, Ammar.
Oh,
Faith, I am with you.
okay. Welcome, Dr. Yusuf.
Thank you,
So
thank you.
Ronak, he's our partner in this research with Ammar. And I received your email right now, so I was very happy. So I want to to convey it to Ronak, because Dr. Yusuf, he sent to me that the ethical approval
Yeah.
document will be sent to us just to fill it, and then after that we will submit it to DHA, Dubai Health Authority.
I like that. That's a great news, Gate, and I'm really thankful for the professor. And I think that we will able to do a very good thing for humanity and masses at the end of the day.
Okay, so welcome, Dr. Youssef. We have also our second speaker, Jan, also with us. I will just go briefly within the architect that we make it for this project. I think already I explained to Dr. Youssef previously, but for the others, and also there is some ideas. I think everybody will be eager to discuss about these ideas because I have also some ideas about how to collect more labor data. So I will share my screen right now just to start my presentation, which is the technical part of this research, detecting COVID-19 by X-ray, especially by X-ray, because the cost of the X-ray, it's less. So mainly, I'm not starting from zero. I'm starting from one or more than one research already done in the world. And because of that, it was easy for us just to start with this because there is a lot of open source data sets. I'm trying just to open the presentation because it will show some ideas. Okay. So I will start just explaining about which data source we are using. So um, starting from the data source, okay, sorry, there's something happening here. Okay. Okay, we'll start with the research life cycle. The research life cycle starting from the planning. The planning itself, it comes because we have an idea about some research happened in the world, especially the most, let's say, excited one. It was Linda Wang from Waterloo University in Canada, and also Dr. Muhammad Farouk from University of Alabama with also cooperation with other teams. This research, it was really excited because the first one was suggesting CNN convolutional neural networks to be to detect the COVID from X-ray. And the second one, it was answering this question to tell them that we have ResNet 50. It's very suitable structure for this. So starting from here, we find that there is some missing point on the two researches that maybe we are able to cover. So the target is we have to have fast and accurate automated detection for COVID-19. Fast and accurate. This is the most important. Fast, that means within seconds or 1 minute, and accurate, that we are sure that if we tell the patient that you are free from COVID, that he will be free. At the end, did we reach that or not? It's something else. What is the tools that we use? It's TensorFlow for sure, with .NET framework, with machine learning .NET library, and .NET Core for the front end, for the back end and front end. It was Angular. I think it's up to the team. This is not my part. Now, what we have a set of X-rays. We claim that we are on the production part, but right now during the presentation you will see that where we are reaching. We have the data source. We have two major data sources. The first one is COVID City Challenge on grandchallenge.org. This is a CT scan images, slices, belong to COVID and non-COVID patients. And it's labeled, it's very trusted, and it's giving us a good start. We have around 700 slides. 300 of them or 200 of them, it is a COVID, and the other is non-COVID. And then we have the Linda Wang and Alexander Wang COVIDNet paper. And mainly they are using three major sources for the data. The first one is the Kaggle Pneumonia Detection Challenge. It started at 2018. And this one, it's a very huge data set. Not very huge, but for us, because it's the biggest one for our research. It's around 14,000 image, but it's related to pneumonia. And since it's 2018, that means there is no COVID cases on it. And the other one is COVID radiology data set. Also, it's on Kaggle. It's already there. And also other open sources, just X-ray data sets. And all of this together will give us the following spreading for the population. The data set itself, it's contain all of these diseases, and it's totally imbalanced. So we have 650 cases as COVID, and in general, it was 8,000, we use 8,000 case of non-COVID. Now, why we make it as COVID and non-COVID? The other researches was focusing on either it's COVID or pneumonia or normal situation, or the other also some research it was focusing on pneumonia, SARS, COVID, and normal situation. But we found that we are facing right now COVID-19. So we need to raise the sensitivity for COVID-19 and to raise the negative predictive value. So for sure, if the negative predictive value is high, that means when the system or the model tell us that this patient is negative related to COVID, we will be sure that really he is negative related to COVID. So in fact, we try to classify the images for us into two classes only, COVID or non-COVID. Anything related to pneumonia, SARS cases, all of this, it goes to non-COVID. Now, how this will help us? Because since we are using on our research, we are using softmax as the output. So we have two outputs expected, the COVID and non-COVID. And all other cases coming to non-COVID. So we have to raise the sensitivity. Then we have to balance the data related to COVID. So in case we have four classes, then we will accept, for example, if we have 1,000 image, we will accept 254 COVID, 254 pneumonia, 254 SARS, and 254 normal. But in this case, we are trying to balance the data with a lot of images related to COVID to meet the total 8,000 image for non-COVID, which is covering all other situations. And most of them, they are coming from pneumonia situation. So the philosophy or the target for us, if the system tells us that the patient is negative, we will be sure that he is negative. He don't have infection. Still, we suggest to make another test after 5 days. But that means we are almost 100% sure about it. If the system tells us is positive, then we are suggesting to make a PCR if it's possible. And until the PCR results it comes, he will be isolated. So that means also it's protecting him from, let's say, coming to his let's say to protecting him from joining his family, from infected his kids or his wife, whatever. So if we have the result within 13 seconds, which is our scenario, so we are able to isolate the patient until the PCR result is coming. So this is the philosophy behind it. This is what our target. And I explained this, that means it's already explained. Now, according to our data set, we have for each COVID image, we have 12 non-COVID images that it's belong to another diseases or it's normal cases. So it's totally imbalanced data set, and we have to work on balancing it. So how to do that? We have first one is remove scripting from the X-rays. How to what we are doing, if it's possible for sure. We have I just go through another script detection algorithm just to find if there is any letters. We will remove the 10% from the top of the image. So that's give us some good results on just removing the scripting. For sure, we keep the original images and we add another image for each one for COVID cases with non-strictly. So this is give us 100% extra that we reach 1,200 image for COVID cases. And then we rotate for 15 minutes according to the suggestion from the paper from Muhammad Farouk, from Dr. Muhammad Farouk, University of Alabama. So we do the same, that we make a rotation for 15 degree, just kind of for data augmentation, just to raise the samples for the COVID cases. And we did some resampling. According to that, what we reach that we have 8,000 non-COVID image and 3,500 COVID image. So the situation it was we have to use weighted loss function. Right now, this scenario for that audience that coming from AI for medicine specialization, this is just a kind of pure example that what we have there in that specialization, we already did it here. So, and then we split it into 80 and 20 for train and test set. And what we did also, the 20% of the images, we keep it for the testing. We didn't use it for any training and any validation. Now, the 80% for the train, we use the k-fold method for the evaluation, so we get the most, let's say, possible impact from this data set. Now, while splitting this, the algorithm is built in the way that there is no data leakage. That means if the images is belong to the same patient, more than one image, so it will be considered on the train or test set without joining the same patient on both. And also, there is no bias about the gender, nationality, imaging technique, and the countries, whatever. There is no bias about this. So it was randomly, totally randomly for that. And because we run this for two models, for Inception version 1 and for ResNet 50, so we have to scale the images into, for Inception, it was 244, 244, and 3. And for the ResNet, it's 299, 219, and 3. So this is the scaling that we are preparing. And then after that, we build the model in the way that it will get the image and then make the scaling the system itself. So we don't have to make a bulk scaling each time we are having a new image or a new data set during the process of the training or of the prediction, the scaling, it will done automatically. Now, the experiment, it was on two models, but with a three experiment. The first one is Inception version 1. The result, it wasn't that much happy. I will share the paper with you after the event. You will find that why we are not happy with the Inception version 1. Then ResNet 50, and then because that it was promising result for the ResNet 50, we expand our X-ray. There is a lot of details on how we where we start and then how we expand our X-ray usage, and we go for the ResNet 50 for the second time. And this was the final result for our model. Now the accuracy, the total accuracy, it was 98%. The sensitivity, it was 99% almost. Specificity, it was 79%. The F1 score, it was 98%. Negative predicted value, it's 99%. Positive predicted value, it was 96%. So mainly we reached to the point that we will tell the people that our model is really promising. Now, what we did also, we go to the production part, to the software architect part. So I will mention briefly what's the software architect that we prepared for that. First, the technology and the environment, it was, as I told you, we followed the .NET Core for API building. And then, because this API with the proper authentication, it will be reachable, and the integration part, it will be possible for any system. So that means we are not building our own system. That API itself, it will be published, and then if any hospital or any organization registered for us, we are ready to give them the credential reader, and then they are able to create their users, and the users will be able to raise the image, get the results, and also provide their feedback, because we are planning to expand our data sets and retrain the model on regular basis according to the feedback from the doctor. So at the end, if our system tells that this is COVID and then it's non-COVID, this will give us more accurate data set, more accurate labeled data. Then the control panel, it is if they are not using their system and they want to use our web interface, they have control panel will help them to specify their specification, their users, the branches, if the hospital or the data center, test center have more than one branch. And all of this, it will be able to done with the control panel, and the control panel is provided with the dashboard to tell them how many cases they receive, how many cases is detected as COVID, how many cases non-COVID. And all of these data sources, it will be connected to central data source to tell that this is the finding of our system, that this is the COVID cases, this is the spreading of COVID in this area according to our system, because all the center is there. So the structure is already there and the system is already there. Also, we provide using microservice architect to make API proxy and to structure the server in the cloud. So we will be sure that there is no more than 3 users for one physical API is calling the API. because otherwise the proxy it will make, and the architect it will make scaling for the API, and then another API it will be created, and all of them it will be connected to the same central, let's say, storage. But at the end, the API itself, because and it's asynchronous. Right now, if I run the test, it will be synchronous, but this is on my local machine. But the structure that we built, it's asynchronous. I received one message. Just let me check who. Okay, I will continue right now. Now we have some reviews to this. Okay, I'm sure that Ronak tell us they are ready, whatever, but we have some resource, some reviews. The first one is the data source. The data source that we have, it's coming from all over the world. But if we are talking about India, we don't have enough cases from India. If we are talking about UAE, which is or Dubai, which is the place that I'm living in, also we don't have enough cases from UAE. The cases itself on the data source, the patient status for them, most of them they are able either they are recovered or the imaging part, the X-ray part, done before detecting the COVID, or it's an early stage of detecting the COVID. So in these cases also we don't have enough COVID cases from the life. So this is why we are sure that the structure, we have very promising results. The system itself or the model itself, it's able to differentiate between pneumonia, bacterial pneumonia, and the COVID pneumonia. But at the end, to use it, 1%, it's not enough for the life. So we need some cooperation with any authority, with any research center or hospital, to provide us with this data, to work together, to retrain and test the model more. And then when we have this, we are sure that we will be able to go for the live. The results, it's very promising because not only the sensitivity, it's also the time. Within 13 seconds of uploading the image, you will get the result that it's COVID or non-COVID. So all of this deserve from us to work on that. And right now we receive good news from Professor Yusuf. I will ask him also for a word or speech from his side. Tell us what is the, let's say, the terms or the constraints for the scientific research, what we have to keep eye on when we are doing scientific research. Also the dataset size. Right now the dataset itself, it's not balanced. We balancing it, but at the end, are we sure that all the patterns is there for the COVID cases? We make a lot of resampling, a lot of data augmenting for COVID. Is this is enough to have trusted? For non-COVID, we have, as I told you, we are able to expand it to 14,000 for non-COVID cases, but for COVID cases at the end, we still, the cases, it's only 650. And the other images, it's coming from augmenting or resampling. So this is the main review for that. Now in the future enhancement, if we are able to get this data set and test the model, for sure we will go more to make segmentation for the COVID or heat map, which is already I did it, but I didn't mention, I didn't raise it yet. Just to provide a heat map to the COVID cases, that if the model detect this is COVID, it will come heat map, and then special area in the lung, it will be highlighted that this is the place that we have infected. Also, we are able to run multitask to make the model able to diagnose more than one disease. We are focusing on COVID for now, but for sure, since we have the model and if it's tested, we are able to go for pneumonia and for other diseases, whatever coming from the lung imaging, it will be there. Also, with the transfer learning, we are able to make it for any disease going to the X-ray. By the way, the transfer learning playing main role here because Inception, version 1 or ResNet, both networks that I use, it was pre-trained for categorizing images for 1,000 plus. And then after that, we add our final layers to make it for COVID cases. So transfer learning main rule here, and also we are able to, for example, for any other diseases or cases, medical cases that using X-ray, we are able to use it. And why X-ray? Because it's cheaper, it's more spread, and it's faster for the normal basis. I'm coming from Syria, my original country. Right now in Syria, daily they are unable to make more than 100 tests only for the PCR. But if they are able to train the radiologists that we have in Syria, we have a lot of radiologists, they will be able to make 100,000 tests per day. If the system, we trusted 100%. Right now, we are trusting it 99%. Okay? So that's why this call for everybody, if you are able to help us with this, we'll be very happy with it. Now, one idea to generating new samples, I'm thinking a lot of it and I'm trying to work on it, but I need the expert to tell me if it will work or not. It's to use style transfer, just how to generate the art if you know about the idea. Style transfer is you have to use a picture as a style and the other pictures would be modified. So if we use X-ray for COVID case as a style and non-COVID case as the, let's say, the sample, and the result it's coming from this, I hope it will be X-ray that showing the style of COVID detection, COVID infection. So this is an idea. I'm not sure about it, how it will work. I'm working on it. And if I get the result, I will share the results with everybody. If this one, it's able to help me to generate new cases. For sure, the patterns, it will not be new, but at the end, it will be new cases. I will work on it. It's kind of imagination. I'm not sure if they'll work or not. But really, it was the last solution for me until right now I received the good news from Dr. Yusuf. So this is about our research. Thank you. We are open for a question right now. So please share us your ideas. I have one question. What is the actual resolution of the X-ray via scaled image? Seems like the test image has much less resolution. No, the actual resolution, it was higher. And according to that, we have to make the scale. No, it was very much higher. And it's different. It's not only resolution. No, because the data source is different. Any question from everybody? I will cover one point related to that until I receive another question. So you are able, please feel free to also speak to us, not only writing through the chat. You are able to unmute yourself and ask your question or share your ideas, because not only question, we need your ideas also. One point, it was how we cooperate with Professor Yusuf. Professor Yusuf, he is the president of Rochester University in Dubai. And Ammar, my friend, and he's also part of the team here in Dubai. He just, because he is student on that university for the master right now, he is graduated. He just bridged this between us, and I explained the ideas, and he make very good help for us. In fact, I really appreciate his help. And right now, I will ask him just to give us brief, as I told you, Dr. Yusuf, about the terms or the constraints for the research. When we are doing research and then we want to go to the production, the ethical part is really, we have how to cover it, especially when you are talking about the medical research, and also in general, when the research or the work is become considered scientific, really scientific research. If you are here, Dr. Yusuf, I will appreciate your share with us.
Thank you, Ghaith, and I would like to thank you for inviting me to this webinar, and I would like to thank all my colleagues listening to me at the moment. I think in my previous research, at the moment I am the president of the university, but my previous research was using different kind of feature recognitions, whether from signals or from images, to extract features, then after that feed them to a classifier. And my main work was using neural network classifiers. And I applied it into various medical systems like prosthesis control, brain signal analysis, and at the same time to industrial and quality production lines. At the moment, as you know, COVID-19, everyone is interested in really doing the diagnosis whether a person has COVID or non-COVID. And Dubai Health Authority, they are really interested in order to find a solution, because they would like to help themselves and help the people and maybe lead this domain in finding a solution of RF diagnosis. So they approached various universities. One of them is RIT. We are a branch of an international university in New York, and we are focusing on technology. And the idea for them, if you have any special way of solving the problem, let us know. So at least we can together, the Dubai Health Authority and the university, in order to find a solution. And then after that, dissipate it to other people. So when in a meeting, Ammar came and he said, look, I would like to work on this. And I came to know Ghaith and we came together. So we met with Dr. Bassam, who is the head of innovation at Dubai Health Authority. We gave him a brief idea, similar to what Ghaith just gave now. And they said, okay, let's consider it. So I think they had their own internal discussions. Then they came back to us recently saying, there is an ethical form which we need to fill. They have to fill, we need to fill. If the individual has to fill, because this is data and personal data, and to share it, you have to go through the process of ethical endorsement. So the form, we will get it very soon and we will fill it. Every individual who will have access to the data has to fill this. So it's not an open source data, which can be used by anybody except those actually that they sign the ethical form. Of course, this ethical form, we will sign it maybe initial team, but after that, if other people from the people attending, our colleagues attending this call, they are interested in applying something different, they could really, again, apply again. We apply again for an ethical form for them, and then they can use the data. So I don't think Dubai Health Authority, they will make it open, the source, but they will be able to give it, and they will be willing to give it to anybody who shows a good idea and can sign the ethical form. Signing the ethical form doesn't mean actually already they approved giving us the data, just only they would like to get more information. And after that, it goes to the IRB ethical committee in DHA. And hopefully they will give us the authority to use the data. We are asking them anything around 3,000 to 4,000 images of COVID-19. And I think that will balance whatever we have on the open source of non-COVID-19. As you mentioned, Ghaith, from my previous research, which all of us, we agree, conditioning the data, cleaning the data is very important. Now, having the same image, but doing various rotations for it or segmentations or whatever, it's a good to increase the numbers, but definitely always people will be very worried. You are actually creating images from the same images. So I wonder whether your accuracy is right or not right. So always there is that fear whether this is right or not right. When it comes to the medical field, people, they don't accept any tolerance of mistakes, because at the end of the day, these are lives. So we have to create more data. We have to increase the accuracy. Maybe at one stage, maybe the data for testing has to be greater than the data for training in order to make sure that it is right. In my previous research, I saw many papers where actually the training data, the testing data, they just keep clustering them, and you will end up confused whether the testing data, the accuracy is for the testing data or a combination between the two. I think with the medical data, we need to be very careful and to have more accuracy, and this needs more images, and images which are actually not manipulated except to clean them up. Medical, assume, for example, we get a solution, and the solution, the accuracy is very high. No hospital immediately will say, okay, let's use it. It will go through again another process of testing just to make sure they are comfortable. And after that, maybe at one stage, they could apply it onto their data and maybe to Abu Dhabi and the rest. And then it goes beyond that. So I think it's too early in order to reach that stage, but at least it's a very fruitful exercise that we should do because it will help. I think this COVID-19, any process, any new analysis, feature recognitions, classifications we can develop can be used for other problems, not COVID-19, other future problems that we could see in the future. We are optimistic now. We managed to convince them that we have the merits, that we can really develop an algorithm, package, a software that really can detect COVID-19, but it needs more testing. I think this has been a good achievement in convincing the people at DHA of that, but still we need to do more work in order to achieve the right results. Is that right, what you wanted me to speak about?
Thank you, Dr. Yusuf. That's perfect. First, I'm very happy with this. I'm very happy that you are joining to us, and you also briefly give us the good, let's say, idea about what's happened and what's expected in the future for this. And in fact, we as a team, we are not expecting to start using it from the hospital. We are expecting cooperation with the hospital to expand the data source. And right now, there's another initiative coming from other part of the world. It's from RSNA in USA. They are also trying to build a robust data set for COVID. It's not only for X-rays or CT scans. It will be multi-dimensional data set that in all kind of information to be. So we in Dubai here and also in India, they are a leader on the software field and computer science. And Dubai, they are a leader in everything. And we are very lucky that we are living here. So together, if we are able also to initiate this, we have this model and we can expand it, test it, and make it better. So your help and with the DHA doctors, Dr. Bassam and also Dr. Bastaki and others, together, if we are able to give life to this initiative, that will be great. So thank you for your help and
Jo-
thank you for your speech.
Uh, thank you, Professor. Thank you for your speech, and I truly appreciate what you are doing. Will serve the cause and the purpose of humanity at the end of the day. Uh, uh, Gates, there is a question from Joseph. He
Yes,
is asking.
yes.
Yeah.
I want, George, if you are here, if you are able to just give me your idea about the class weights in this case. Because, as I told you, I didn't use it for like more than one classes. We have COVID and non-COVID. It's two classes only. So at the end, the weighted loss, it will be just like the class weight, according to my understanding. So if you are able to help me with that, please speak us your please advice. George? Hello. Yes, I think George, he is not here. According to my experiment, because we keep it as two classes only, which is COVID and non-COVID, so the weighted loss, it will make the class weights. It will make it like this. So if we are trying to classify it more than two classes, that means we need to classify each diseases at that time, we have to move to class weights. Also, why we use it, and by the way, it was possible to do it just like binary classification, that this is COVID or not, and go ahead. But we choose to make it as let's say, as just like image classification with two classes only. So we are not trying to find the pattern for the COVID. The network is trying to find the patterns for COVID, and all other non-COVID also will try to find the pattern. So if we lose the accuracy for less because the COVID cases is less, we will be sure that we have good accuracy because the non-COVID also they are discovering the pattern. So that's why this is, I think, this strategy, it's raised the accuracy for our model. That's why we have this until now good results, which is 98% accuracy and 99% sensitivity. So any question, please? In case there is no question, I will go to Dr. Janjits to give us another example about the production part. They do the same thing in terms of measuring generalization performance. Okay.
Hi. Yes. Thank you.
Thank you. Thank you, Jan. Please introduce yourself and
Yeah.
it's your time. Thank you.
Okay. Thank you, Guy, for a very interesting talk so far. I'm very excited that COVID-19 detection is, of course, one of the most important things in the world right now. And I'm very happy to hear about the improving the performance and making it cheaper. So I will give a short presentation about what we can do about using AI in smartphones to also detect health problems. And I will keep it a bit more general because I'm currently not working on anything specific here, but I'll share some of my experiences here. So what is personalized healthcare? Why do we do it? So every person is unique. So the idea is that healthcare should be unique to each person as well. The benefits can be enormous if we can tailor medicines and medical advice and treatment for each person's. And of course, doctors do this already to some extent, but doctors cannot help everybody in the same way currently. Rich people who are able to buy more time and better health insurance get better treatment. We should be able to do this for everybody. Personalized healthcare, typically people think about genetics, but it's not just the genetics. It's also it's environment, lifestyle environment matters a lot for personalized healthcare. So if you're just not who you are, you're not the same person who you were when you were born. You develop yourself and you develop your own traits and your own weaknesses and your own strengths, and these should be part of personalized healthcare. So personalized healthcare needs lots and lots of data. You need to be able to distinguish each person, and you need to be able to say something useful about their health. So this needs a lot of data. And this data also needs to be up to date. So something you had 10 years ago might be relevant, but so you need to know what happened last week or last hour. And doctors are just not able to interpret all of this data on time, and also not able to compare it to everybody that you want to be. Yeah. Your even your own family, they might live in a different town. Your doctor might not know what their health problems are. This sort of thing, this doctors just cannot do. So this is where machine learning and what I'm going to talk about, how to use smartphone data here. So this is able to make a sort of extra biomarker. So you could think of it as AI terminals. So actually, I read a story last week about how thermometers for detecting people's health were a big improvement for enabling healthcare for poor people, because previously only mostly wealthy people, everybody went to doctors in the 19th century, but only wealthy people, educated people were able to talk about their problems in a way that doctors were listening to. And now when you add objective data to this mix, everybody suddenly got better health, because doctors were able to measure objectively what the health of a patient was, and they didn't have to listen and interpret in a way that made sense to these doctors how their health was. So this is very very big improvement. And the idea is that we can use machine learning and smartphone data to make better thermometers that say a lot more. And this enables more democratization of health. So a person can, so all this data, where does this come from? So of course, everybody now surrounds themselves with smart devices. So I think many people, almost everybody now has a smartphone, which monitors a lot of data. You can also think about, many people nowadays have sometimes small medical devices. And is everybody? So these small medical devices, they're sort of, expensive, small, but they can add a lot of. And of course, you can also talk about self-monitoring. So people can describe how they feel each day. They can describe what they eat, how much they weigh. And this is also, of course, very useful for getting data. However, one of the big problems for this type of monitoring data is that outside of research purposes, people tend to not want to do it. So it should be, if you want to have continuous monitoring of people, it should be low key, it should be a low barrier entry. And what you can see is that this is a typical big problem of using personalized healthcare, is that self-monitoring and using these small medical devices, they have a high threshold of usage, and so they have a very low adherence. So people tend to do this if they really, really need. So for example, the glucose meter, which is visualized here, this is typically used by people who have diabetes, but people who don't have diabetes yet, but are at risk of getting it, they don't tend to use it. And of course, it's also more expensive to use. Well, almost everybody has a smartphone. So the use of smart devices, smartphones, which everybody has, is a very big opportunity for healthcare. So, yeah. So what does that mean for what data can we gather from smartphones? It's actually smartphone data contains lots of information on health of people. So it doesn't contain a lot of other information, so you cannot use a smartphone to take X-rays then, but you can use a lot of other things. You get a lot of other data from this. So for example, you get movement data. Movement data doesn't seem very medical at first, but think about it. So how fast you walk is a very good indicator of your health. If you walk fast, you walk full of energy, you're probably healthy. Walk slow, you have trouble getting upstairs, you walk slowly upstairs. Typically, that's a sign of a health problem. Voice data. So every smartphone, by definition, has a microphone. So you can record voice data and actually how people sound. You can hear if somebody has a cough. You can hear if somebody has trouble breathing. You can some diseases actually. I heard of a case where one of the diseases typically leads to a nasal voice. You can try to detect that. This sort of data, this is very easily accessible with a smartphone. Facial expression. If you look at somebody, you can see if they're tired. A phone with a good camera and a good machine learning algorithm can also can see if you're tired, if your eyes are still okay, if your facial expressions is okay. This sort of thing you can easily do with a smartphone. This sort of data and this combination of data by using it for continuous monitoring, every day you take a snapshot of your face and record some sentences, and you keep your phone with you and gather the data of how you walk. You can get a very good idea of how healthy somebody is, and also what kind of if the person is not healthy, what kind of problems there are. And this can be used for yourself to go to a doctor to say, okay, I'm not feeling healthy. You can tell to the doctor, but I was walking 50 meters per minute last week, while normally I walk around 100. Just cannot get ahead. So the doctor then knows, okay, maybe there's something wrong with the cardiovascular system or with the legs. So what can we, what kind of machine learning algorithms can we use on this thing? So for example, one example use case is, this is, unsupervised learning. So we can identify clusters of people, and if we're doing, for example, a controlled experiment of a medicine, we can cluster these people into different groups and see if these different groups correspond to positive or negative response to the medicine. For example, you could have group A has no effect. Group B has a positive effect, and group C, actually, you should give medicine because they have a strong negative side effect. So now, if you have this medicine on the market, you can look at, okay, we give these people, we monitor this group of people that are in need of this medicine, and we see, okay, this person belongs to group B. We should definitely give this medicine. And maybe group A, we should give a different medicine. Group C, we should never give that medicine. This sort of thing is possible if you have this ability to monitor. But this requires, actually, it's unsupervised learning, but this requires an experiment before. You just cluster people. right? You can cluster people into different groups. That's easy to do. Everybody can do that. But are these different groups relevant for their health? That's a question you have to ask before. So that's something where you need a controlled experiment. A different example use case is, okay, let's say we have a lot of supervised learning. So if you have a lot of target data, so for example, a lot of people that have measured blood pressure, and somehow you want to detect that using a smartphone. I don't think you can measure blood pressure data, but some other, for example, you want to measure how well people and what that means for their health. So you can use smartphone data to train classical supervised learning algorithms like neural networks to get this outcome. And this is very advantageous. So you can use a smartphone then for cheap continuous monitoring. Yeah, you can also easily, rapidly spot problems. So if a person suddenly starts walking less, if you detect it with the smartphone, you can flag something, or you can warn the user. Or, for example, if a person suddenly develops a different voice, maybe they should go to see a doctor. If something is wrong with their illness. Yeah. On the other hand, typically the training data is very hard to get. So you need to have representative training data, and typically even gathering data for medical purposes is very, very strictly regulated. You can't just say, okay, I'm gonna go to 100 different patients and give them a smartphone app to monitor them and then measure them. This typically needs review by an ethical board, and yeah, you have to go through a lot of steps here. Regulations are pretty strict, and also what I found in the past when I was doing this kind of experiments is the reliability of clinical data and the validity is not always that good. So, for example, blood pressure, of course, you can easily measure, but let's say you have a continuous monitoring of a patient, how well they walk. So you every day in a week measure how well they walk. Okay, so with the smartphone. Now they on Friday they go to the hospital and their ability to walk is measured. So is it representative of typical day? Of course not. So people have to go to hospital and they feel different. How they walk on Friday after going to the hospital might not be representative from how they walk on Monday after a good rest in the weekend and they're at home. So the reliability of this clinical data is typically a large problem with this use cases. So you really have to think about how reliable is my target. And yeah, because you're trying to replace this clinical data, you typically have a use case that you can, this clinical data is expensive to get. So you don't have a lot of it and it's not reliable. So this is a, typical challenge for this use case. Another use case that is very common, quite common nowadays, is anomaly detection. So you monitor the patient and suddenly something changed. Now, this change might be benign or it might be harmful. So here, for example, you see heart rate monitoring and suddenly there's a skip in the heart. You might want to warn the user of it. So typically you have an anomaly detection machine that you use that can tell you if something is anomalous. And this actually, I know Apple in their Apple smartwatch has been doing this and actually warning people with heart problems. And I have also heard stories that this type of thing could be used if you have, let's say, a month of monitoring data for a patient, that this could be used to detect COVID-19 actually. So people were showing signs of COVID-19 before they were aware of it themselves, but this type of anomaly detection using smartwatches could actually detect it before they knew it themselves. So this is advantageous because you don't need a very large data set, and it can touch a large variety of problems. Anything that is out of the ordinary can be detected by this. Yeah, this is quite handy. However, one of the challenges, of course, is this is very hard to tune correctly. So, what do you mean by anomaly? And what is the? And here you have to think about what is the cost of a false positive and a false negative. For example, false positive for heart attack. Okay, so people are warned, so you don't want to do that too often. The false negative, of course, can be really, so you say everything is a-okay, so the person doesn't go to a doctor, but actually you have a heart attack. So you have to really think about it. Also, of course, you don't want to have too many false positives, because then people will stop believing your algorithm, and people will stop going to the doctor when they need to go. And it will place a burden on the healthcare system. And yeah. So it's really hard to say that you have an anomaly, but is that really something to worry about or not? So this is typically very hard to tune, especially since anomalies by nature are very rare. So you typically don't have a very large data set of anomalies to tune your algorithm. Another one that I encountered at some point was another use case is using reinforcement. And this is a bit of a funny thing, because here, this is a not very common use case for reinforcement learning, because here, well, reinforcement learning is you observe an environment, you interpret it, and then the machine learning algorithm takes an action and then learns from it again. So it takes an action and sees, okay, what is the environment after taking my action, and do I get a reward for this, and how do I improve? Now, what happens here is the environment is the patient, or the person itself, and the data that comes from this. Let's say, okay, so the use case here was we had a supervised model here that interpreted this patient data. So it said, okay, the patient is healthy or not. Okay. And now the agent was giving an action. So the agent is the reinforcement model as advice. So it said the patient data here was glucose monitoring, and it said, okay, if you eat this, your glucose will jump. You'll feel good at first, but then after a while, there you're get a sugar crash, and you will have less energy. So my advice is now is to hold your hunger for a while and don't. So this is a very interesting use case, because here the environment is the patient, basically a machine learning algorithm is telling people, eat this or don't eat this, or eat some sugar now. That's a very interesting use case, I thought. So this is a very powerful method for changing lifestyle for the better. So the idea is that of course you don't have to do this forever. So you will just reinforce people's habits, and at a certain point they will do it themselves. They don't know when not to do it, when to. So they will learn themselves. But of course, this is extremely challenging. So, for example, people will not always do fast. So people say, okay, the machine tells me not to eat, but I'll ignore the machine. I'm just hungry now. How do you deal with that? So how does this model deal with that? That's a very challenging thing to train on. You also have a very stringent safety boundary. So you don't want to tell people to jump off a bridge, because the algorithm says so. You don't. The algorithm has to has to be very strictly bounded to only give safe advice. And I don't know how much everybody knows here about reinforcement learning, but typically reinforcement learning training is very tricky, right? It's a very the methods don't always converge. There's a large chance of a model going off the rails and then going into some state always saying the same thing or giving correct advice. So this is very tricky to get right. But if you get this to, this is a very powerful method that people can use to get their own personal health advice and get into healthy habits. So these are some example use cases that I found. Yeah. So what are some of the overall challenges? So privacy is a very big challenge, and this is of course also related to the regulations, but here I want to specifically talk about this because smartphone data is by nature privacy sensitive. Just don't want everybody to know what is on your smartphone and how healthy you are. On the other hand, if you deploy such an algorithm, you want to keep monitoring if your algorithms are still up to date. That's very important because maybe if everybody gets sent home in a lockdown and suddenly your algorithm starts giving advice, go outside, go outside, go outside. That's not right. So you have some tough decisions to make how to process your data, especially not just the training data, which of course needs to be anonymized in a certain way, but also the customer data, so the client data of the patients. So there are some ways to deal with this. You can have a strong central server with very strong protections, only certain people can access it. Of course, but this is typically, do you want this responsibility to have this data of these people here? You can try to anonymize the data, but this is also tricky because, for example, you're tracking movement data. Can you really anonymize this? If you know where somebody moves, you know where he lives. You know this. So you can also try to keep the data on the device. There's a possibility of something called federated machine learning, where you have, for example, this is a tool of federated machine learning. So you have a central server, you have some model, and now if you want to update it, you transfer this model to several nodes, which are typically then smartphones themselves. They get some extra data, and you ask some people to check if this data is correct and to correct this data and provide some labels. And then based on these local trainings, you update, they send updates of these local trainings to the central server, and then the central server can update it without accessing any of the private data of the phones. So this is one possibility. Of course, you probably have to do a combination of all three to get really the privacy correct. So to conclude, last thing I want to talk about is some of the risk. So if you want to use a smartphone to monitor health, it becomes a medical device. And as Guy and other speakers mentioned, this you need to the medical devices are very strictly regulated typically. So one of the things you typically need to show depends on the exact country you're in, but you need to show and document that the device has a real benefit and it doesn't have any additional risks. This is something that's typically new for the AI community, but especially the risk. And this needs to be documented. And there's all kinds of rules and regulations on this, and this is really, you need to get a proper trail. You need to have documented which people did you test it on, what were the outcome, which was the training data, what you think the training data is representative of the real environment, and what happened if did people get hurt using your device. That sort of thing. Of course, the privacy concerns I already mentioned, and one other thing is that actually one of the risks is people want to, you want to, well, unless you have a large fund, maybe, you need to be paid. for these medical devices, so who's going to pay? So this is going to be covered by insurance, and they typically have some additional concerns about what is in it for the insurance, what is in it for the patient. It can show benefit to the patient, maybe they will, but this is something that you need to think. It's not immediate that people will pay for it. And yeah. And actually, I also want to make sure that so you need to make sure that your training data is representative of the target audience. So if you have if you have a group of people that come and that you can ask a lot of people install the phone or install a phone and then monitor, but this is really representative of the type of people that you're targeting. So, for example, there's a lot of unfairness in machine learning, and especially for medical devices, this is very tricky. So, do you have enough people of all age groups? Have enough people from all the genders? Do you have enough people? There's a racial bias in your training data, and this will give a big risk of your performance. You need to make sure that your training data is really representative target audience, because otherwise your device will give the wrong outcome, and especially for health devices. Okay, so the conclusions. Well, I didn't touch on this, but as you can imagine, personalized healthcare can be a huge market. So some estimates of over $3 trillion 2025. So this is a huge opportunity for AI to get into. If you can show that your device, your smartphone, is able to help people, there could be a lot of money there. And also, of course, a lot of savings for better health. The smart devices we currently have, they gather a lot of data that can be used for personalized healthcare. If you have a new use case for this, you can easily augment this by some specialized devices, glucose meters, oxygen meters. They don't need to be that smart, but if they can communicate with a smartphone, the smartphone can gather the data and process it. And there's many different options for this, for the use of this data, from nudging people to healthier lifestyles to maybe warning people of impending heart attacks. And because medical data is so sensitive, you need to take extra care of the fairness, privacy, and also that you can interpret it. Doctor needs to know why a device is working. So maybe the doctor can interpret, needs to be able to explain to the patient why they're at risk of something. Otherwise, the patient doesn't really believe. Okay, so that's what I wanted to say. I hope everyone stays healthy, is healthy, and thank you again for listening, and thank you again for the opportunity.
Thank you, Jean. In fact, I have just two comments about your. It was a great speech for sure, but I have two comments. The first one, if reinforcement learning, is it? I have a conflict, in fact, between the lifestyle, let's say the healthy lifestyle, and the enjoyment lifestyle. I don't like healthy lifestyle, so this is my problem. And the second one, in fact, it's serious. It's not a joke. It's about who will pay. Just like this personalized healthcare, I think it will be following the same of the social media track that the sponsor promoted who will pay about this. This is in the future for sure, it will be sure, but yes, really it's challenge, and but how to go through it, yes, this is how it will be happen. And in fact, this is, I think it's easier than the future of this personalized healthcare it will be easier than the diagnostic models that using AI. That one, it's very critical because it's really working with the privacy, immediately the privacy of the patient, with the privacy of the data. And right now, you can see from the Yusuf that we have to sign this ethical code or ethical agreement before we get this information, this data to train it. And then also when we go to the production and how kind of there also it will be who will pay, it will be very important. So thank you for your speech. In fact, it was very nice one. And the good thing is you have multiple scenarios, multiple use cases. It's mentioned there. Really, I enjoy it. Thank you. And everybody, if you have any question to Dr. Jan, I think he is waiting for it.
Yeah, thanks. Yeah, so I
No
can give
question.
some.
No, yes.
Yeah, so I can give some. Yeah, indeed. So the reinforcement learning, that's a very good example of the non-adherence, right? So if you are given advice for a healthy lifestyle, but you don't like it, so you also want to enjoy yourself. So it's very tricky to get this correctly in a machine learning model. So the machine learning model doesn't know about enjoyment automatically. It knows only about how hope.
Yes, exactly. This is what I tend
Yeah.
to say. Yes. So thank you, Dan. It was very
Yeah.
great. This says if there is no question, I would wrap up all of this. In
Yeah.
fact, I was planning to get also another speech from another doctor to tell us about the approvals for any diagnostic model or any AI model related to the medical. Also, if we are able, I wasn't able to do that, but to just show some scenarios, for example, for FDA approvals or for CA approval in Europe. I don't know, John, if you are able to help us with this. Here in Dubai, I think you find a live example about what we are trying to do to get the approval with the help of the researchers, for example, Rochester University, and also Ronak tell us about the India, what's happening. So we have some samples from all over the world. I hope will meet the target of the event itself. And this session, it will be on YouTube on the same link that's shared with everybody. And I will ask to share it once again. Thank you for joining us, and I hope this was useful for everybody and enjoyment for everybody. Thank you.